When you think about something like Google's search algorithm or how engineers build structures that can withstand earthquakes, the secret sauce often comes down to a code that's buried deep inside matrices. Well, today, we're going to crack that code. We're going to explore two of the most powerful ideas in all of linear algebra: eigenvalues and eigenvectors. So, here's the central puzzle we need to solve. Usually, when you multiply a vector by a matrix, it gets sent off in some completely new direction. But what if there are special vectors? Vectors that are so fundamental to that matrix that they don't get knocked off their path. They just get stretched or shrunk, but they hold their line. How do we find these incredibly important vectors that show us what a matrix is really all about? That's the mystery we're unraveling today.
And here's our game plan. First, we're going to define what this hidden code is actually made of. Then, we'll walk through exactly how to find the eigenvalues. Those are the secret numbers. After that, we'll find their partner vectors. Then, I've got a great little pro tip to help you check your work. And finally, we'll pick up some key vocabulary so you can sound like you've been doing this for years.
Okay, let's dive right in. Look, before you can crack any code, you have to understand the language it's written in. For us, that means getting really clear on what our two main tools actually are. First up is the eigenvalue. You'll see it written with a Greek letter lambda. And you can just think of it as a number, a scaling factor. That's it. It's a special number that tells us exactly how much its partner eigenvector gets stretched or shrunk or maybe even flipped around when the matrix does its thing. And here is its partner in crime, the eigenvector. This is that special vector we were just talking about. It's got this one amazing property. When you hit it with the matrix, it doesn't change direction. It stays on the exact same line it started on. It just gets scaled, stretched, or shrunk by its eigenvalue. It's the vector that truly holds its ground. All right, so we know what we're looking for, but how in the world do we actually find them? Well, it all starts with the eigenvalues, and for that, we need a kind of master key.
And this is it. This is our master key, the characteristic equation. I know it might look a little intense at first glance, but the idea behind it is actually pretty cool. What we're doing is looking for a special number, lambda, that makes the stuff inside the parentheses, that matrix A minus lambda I, singular, which is just a technical way of saying its determinant is 0. So think of it like a puzzle. Find the value of lambda that makes this equation true, and boom, you've unlocked the eigenvalues.
And the whole process really just boils down to 3 straightforward steps. First, we build that new matrix, A minus lambda I. Second, we calculate its determinant, which gives us something called the characteristic polynomial. And third, we just set that polynomial to 0 and solve for lambda. The answers we get? Those are the eigenvalues. Simple as that. Now let's look at an example. The great thing about this first step is how easy it is in practice. All you do is take your original matrix, A, and just subtract lambda from the numbers on the main diagonal. That's it. You see here? The 4 becomes 4 minus lambda, and the 1 becomes 1 minus lambda. The other two numbers, totally untouched. So when we actually calculate the determinant of that matrix we just made and set it equal to 0, this is what we get for our example: a nice, clean quadratic equation. This is our characteristic polynomial. Now all that's left to do is solve it. And after a little bit of algebra, we find our first key to the code. Our first eigenvalue, lambda 1, is 6. This is the first of our secret scaling factors. And the second solution to that equation is 1. And there you have it. Just like that, we've cracked the first part of the code. These two numbers, 6 and 1, are the fundamental scaling factors that define how this matrix behaves. Okay, so we've got the scaling factors. That's the what. But what exactly are they scaling? Now it's time to find the who. Let's find the eigenvectors that go along with these values. So to find them, we start with this equation here, and you should recognize that A minus lambda I part. It's our old friend from before. What we do now is we take the eigenvalues we just found, one at a time, plug them back into this formula, and then solve for the vector x. So let's actually walk through it. We'll grab one of our eigenvalues. Let's use lambda equals 1. We substitute that 1 back into our A minus lambda I matrix. That turns this whole thing into a system of linear equations, and our job is simply to find a non-zero vector x that makes it all true. Now this brings up a really, really important point. We don't find just one vector. What we actually find is a whole infinite family of them that all sit on the exact same line. So for our eigenvalue of 1, any multiple of the vector 1, 3 will work.
So, we usually just pick the simplest one, the space vector, to represent that entire direction. Okay, before we go any further, I want to share a little secret weapon with you. This is an absolutely essential check, a little sanity check, you can do to make sure the eigenvalues you calculated are actually correct. Because if these are wrong, everything else you do will be wrong too. Here's check number 1, and it's super easy. Add up your eigenvalues. For us, that's 6 plus 1, which is 7. Now go back to your original matrix and add up the numbers on the main diagonal. That sum has a special name. It's called the trace. Here, that's 4 plus 1, which is also 7. They match perfect. And for check number 2, multiply your eigenvalues together. So 6 times 1 is 6. Now calculate the determinant of the original matrix. For us, that's also 6, another perfect match. When both of these checks work out, you can be very confident you found the right code. Fantastic. So we've cracked the code, we've double-checked our work. To wrap things up, let's just quickly go over a few more important terms that you're definitely going to run into. First off, don't get thrown off if you see eigenvalues called something else. Depending on what book you're reading or what field you're in, you might see them called characteristic values, characteristic roots, or even latent roots. It's all just different names for the exact same thing. Okay, next up is multiplicity. The algebraic multiplicity is super simple. It's just how many times an eigenvalue shows up as a repeated answer when you solve the polynomial. The geometric multiplicity is the number of independent eigenvectors you can find for that eigenvalue. And the big rule to remember is that the algebraic number is always bigger than or equal to the geometric. And finally, 2 really simple ones. The spectrum of a matrix, that's just a fancy name for the complete list of all of its eigenvalues. And the spectral radius is even easier. It's just the biggest absolute value you find in that list. So for us, with eigenvalues 6 and 1, the spectrum is the set 6, 1, and the spectral radius is 6. So look, we've done it. We've successfully dug in and found the hidden code of a matrix, its fundamental scaling factors, and its unshakable directions. But really, this just opens the door to an even bigger, more powerful question. Now that we have this code, what can we actually do with it? How does this code unlock amazing things like simplifying incredibly complex systems or the holy grail of diagonalizing the matrix itself? Well, that sounds like a story for another time.